We're going to do more practice of negating statements. So I'd like you to grab some paper and find the negation of the following statements and open sentences. So grab some paper, try this out, and we'll talk about them one by one. Okay, at least one of m and n is an integer. So we want to negate this statement, and let's just think about what the structure of this statement is. At least one of is an or statement. So this is negating the statement at least one of m and n is an integer. That means m is an integer or n is an integer. That's the statement we want to negate. We know De Morgan's laws for negating ands and ors. The negation of p or q is equivalent to the negation of p and the negation of q. So if it's not true that m is an integer or n is an integer, then negation of m is an integer and negation of n is an integer, negating separately, changing the sign. This is equivalent to m is not an integer and n is not an integer. And if we wanted to write that in words, m is not an integer and n is not an integer. Or we could write it as neither m nor n are integers. Next, we have both x and y are real numbers. So in other words, we want to negate x is in the real numbers and y is in the real numbers. We want to negate that. Again, by De Morgan's laws, that's equivalent to the negation of x is a real number, and then we flip our sign, or y is a real number, and so, or the negation of y is a real number. And so that's equivalent to x is not a real number, or y is not a real number. And if we wanted to write that in words, x is not a real number, or y is not a real number. We could also write that as at least one of x and y is not in the real numbers. Next, for all real numbers x and y, f of x equals f of y. So we are negating the statement for all x and y in the real numbers. F of x is equal to f of y. We're negating a for all statement. So the negation of a for all statement is a there exists statement. There exist x and y in the real numbers such that f of x is not equal to f of y, such that the negation of f of x equals f of y, negating that. So the negation of a for all statement is a there exists statement, where the second piece of it, the remainder of it, is negated. So our negation is there exists some real numbers x and y such that f of x is not equal to f of y. We could write that too in plain English as there are some real numbers x and y such that or for which f of x is not equal to f of y. A quick note here is that in the original statement there was no such that. So there was no such that in the original statement, but when we did the negation and we had a there exists, we got a such that. So just note such that or for which typically follows there exists statements. So there exists, x in s such that blah, 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 but does not typically follow for all statements. So for all x in s blah, 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 we don't really need such that or for which because there's not a specific one we're referring to. We're talking about all of them. Okay. For any natural number n, there is a set A such that the cardinality of A is equal to n. So we're negating for any n in the natural numbers, there exists a set A such that the cardinality of A is equal to n. That's what we're trying to negate. If we're trying to negate for all, so we sort of negate, we do the negation from the outside in. If we're trying to negate for all statement, that's a there exists statement. So there exists some n in the natural numbers such that now we want to negate the next piece. So we're just going to do it step by step, such that the negation of the rest, there is some set A such that the cardinality of A is equal to n. We want to negate that second piece. So we've got there is an n in the natural numbers such that the negation of there exists statement is a for all statement. So for all set A, for any set A, now we're going to negate this one. For any set A, the cardinality of A is equal to n. What's the negation of that? And so our last step through, we don't necessarily need to do each of these steps individually, but just for clarity in the early examples, there is some natural number n such that for any set A, the negation of the cardinality of A is equal to n, well then the cardinality of A is not equal to n. And if we want to write that out in words, we could write that out as there is some integer n such that for any set A, the cardinality of A is not equal to n. All right, next we've got there is an integer n such that for any real number x, x times n is equal to x. So we're negating there is an n in the integers such that for any x in the real numbers, x times n is equal to x. That's what we're negating. So piece by piece, first to negate a there exists statement, that's a for all statement. So for any natural number n, negation of, now just let's negate that next piece separately. All right, so for any natural number n, now we want to negate the next piece. If we're negating a for all statement, that turns into a there exists statement. So there exists an x in the real numbers, a real number x. We didn't previously have a such that there, but we are adding it. There exists a real number x with the property that or such that. And then the negation of the next piece, if we want to negate x times n equals x, that's just x times n is not equal to x. So again, just as a note, here we dropped a such that. We had a such that, but we dropped it when we turned it into a for all, because for all does not typically have a such that. Here we did not have a such that, but we added one because we turned it into an existence statement, and that typically does go with a such that. So just think about reading these out loud and how they flow. For any natural number n, there is a real number x, such that or for which x times n is not equal to x. So we could say that, if we wanted to write it out in English, for any natural number n, there is a real number x such that x times n is not equal to x. Next, we want to negate a statement of the form, if a function f is continuous, then that function is differentiable. So, in other words, we're negating an implies statement. F being a continuous function implies that f is a differentiable function. So there's different ways to approach this. One is to transform it into a universal statement. So recall that any implies statement, p of x implies q of x, is equivalent to the statement for all x such that p of x, Q of X is true. So we could rewrite this as for all continuous, for all or for any continuous function f is differentiable. That would be logically equivalent to our original statement. And so now we want to negate a for all statement. The negation of a for all statement is a there exists statement. There exists a continuous function x such that, and now we're negating f is differentiable. The negation of f is differentiable is f is not differentiable, such that f is not differentiable. Or if we wanted to put that in words, there is a continuous function f that is not differentiable. So we see that what we've arrived at is a statement of the form, if this is the statement, if this is p, f is continuous, and function is differentiable is q, then we started with something of the form p implies q, and you may recall that that is logically equivalent to p and not q. So we've arrived at a statement of the form p and not q, where f is continuous is p, and f is not differentiable is not q. If that is not feeling familiar, sort of review the end of last video. So end of last video, we showed that in general, the negation of p implies q is the same thing as p and not q, and that's a really useful thing to recall. Next, if a person enjoys reading, then they do not, or if a person enjoys reading, they do not enjoy video games. How could I negate this? I need to find one person who enjoys reading but does also enjoy video games. So again, this is negating a statement of the form p implies q. Person enjoys reading implies they don't enjoy video games. If I want to negate that, one way I could do it, negate a statement of the form p implies q, is p and not q. So in that case, this is there is a person who likes reading or enjoys reading, and negation of q, they don't enjoy video games, so that means they do enjoy video games. Next, we've got another implies statement. Again, here's our p, here's our q. The negation of p implies q is p and not q. So there exist sets A and B such that P is true, A is a subset of B, and Q is false. B is not a subset of A. That would be the negation of this statement.